Hi, my name is Tuomas Mutanen and I currently work as a postdoctoral researcher in the Department of Neuroscience and Biomedical Engineering, Aalto University, Finland. Over the course of the past few years, I've been developing some spatial filtering methods for tackling some of the very challenging artifacts related to TMS EEG recordings. These novel methods have now been included as a part of an open source data analysis toolbox called TESA, and one of the main purposes of this video is to show you in practice how you can take and use these tools to clean your own TMS EEG datasets. In addition, I will go through some theoretical foundations of these methods to help you understand what they are made for and how do they work. So I will give you a super quick introduction to combined transcranial magnetic stimulation and electroencephalography, because I'm sure that for the vast majority of you, it is a very familiar method. So the idea, of course, is that we bring a coil next to our subject's head, and then through the electromagnetic induction, we induce an electric field in the brain strong enough to activate the neurons in our cortical region of interest. Then by following the brain activity simultaneously with EEG recordings, we can, for instance, follow how this initially focal activity spreads to the other cortical regions, and thus we can learn something about the connectivity. The problem, of course, with the TMS is that the electromagnetic induction also couples the TMS pulse to other tissues than just brain, and for instance the cranial muscles, or it can couple the TMS device with the EEG instrumentation. And as a result, we get a number of challenging artifacts in the TMS EEG signal that we want to remove. Luckily, we know quite a bit of the underlying physics and physiology of the neuronal EEG signals of interest. We know that the neuronal EEG signals are coming from the postsynaptic currents, mainly on the cortex, and these postsynaptic currents, they drive volume currents that must travel through the insulating skull, and then they travel through the conductive skull. EEG then is measuring the potential differences on the scalp resulting from these full volume currents. Now, because of this conductive structure of the head, we know that the genuine neuronal responses, they generate topographies that are rather smeared and that have rather low spatial resolution. This is not the case for many of the artifact sources. For instance, the TMS evoked muscle artifacts, they can have topographies that have a much higher spatial resolution. So if we can take this prior information and write it in terms of mathematical formalism, we can use it in a powerful way to detect and remove artifacts from our data. This is done here in the equation that we can see. So our signal S can be written in terms of the artifacts A, the noise N, and then the unknown cortical signals X, which are linked to our EEG signal through the lead field matrix, which basically describes how our different EEG sensors are sensitive to all the possible cortical signal sources that we might have. By using this equation in a smart way, we can remove some challenging artifacts from TMS EEG signal, as we will see today. So the tools we are using today, they work on MATLAB. So obviously the first thing to get started is to find and download the appropriate code. So as I said, the tools are now part of the open access data TMS EEG analysis code repository called TESA. And you can find all the relevant information of the TESA toolbox from this website. And the TESA website obviously has links to the releases, which you can download, and then a very comprehensive manual that explains you how to download and install the TESA tool package, and also how to use the functions for different purposes. If you want to contribute to the TESA toolbox, and then I would strongly recommend to contact Nigel and take it from there. Now the TESA code repository has been implemented in the EEG lab environment, and EEG Lab is then another MATLAB data analysis toolbox. It's very popular among the EEG analysts. And cool thing about the EEG Lab is that it enables you to download various types of EEG datasets almost regardless of your EEG system. And also it is easy to upload the EEG Lab data that you have pre-processed to, for instance, Fieldtrip and continue with some more advanced analysis. The link for EEG Lab you can find here. And then a third toolbox that you need to get everything working in TESA is this fast ICA package, which is basically an efficient algorithm for finding the independent components. And this is the link to fast ICA. Now, after we have successfully downloaded the appropriate toolboxes, we can go to the first method. And the first method we will go through today is so-called signal-space projection combined with source-informed reconstruction, in short SSP-SIR. And this method was originally developed for removing the TMS-evoked muscle artifacts in the EEG signal. So on the first slide, you will see how the TMS-evoked muscle artifacts typically look in the EEG signal. So on the left panel, we can see the characteristic biphasic responses right after the TMS pulse, as well as the topographies that are typical for muscle artifacts that have a much higher spatial frequency than, let's say, neuronal topographies. On the other hand, on the right side, we can see the time frequency transformation of a typical muscle artifact contaminated EEG time course. And the goal here is now to estimate those muscle artifact topographies that you can see on the lower left panel. And we estimate them from the high-pass filtered data because we can see clearly from the right side panel that the neuronal signals, neuronal responses are mainly confined below 100 Hz. And the whole sequence of the SSP-SIR method goes as follows. So first we estimate the muscle artifact topographies from the high-pass filtered data, and we project those topographies out with this projection matrix P. And now you can see that the new equation, the main difference is that we have got rid of the A, but the new equation has the exact same form as the original one. So we can use traditional inverse estimation methods to estimate the cortical sources that will generate the artifact-free signal. And because we have the lead field matrix L and the source estimates now, we can actually go backwards and reproduce the artifact-free signal in the original signal space. So let's then see how this SSP-SIR implemented in TESA looks in practice in our MATLAB. So what we have here is some example datasets where the left parietal cortex has been stimulated. And now, regardless of some very basic pre-processing steps that I've done, it's clear from these both figures over here that there is still some residual muscle artifact left. So from this figure, we can see that there is this early topography clearly coming from the temporal muscles, even though the parietal cortex was stimulated. And it's a bit subtle, but if we check some of these channels in this global EEG map, we have these very fast biphasic responses in these channels characteristic to muscle artifacts. So let's see how the SSP-SIR will work. So we will open the SSP-SIR using this graphical user interface of TESA. These are the default settings. One important thing to note is that you do need the lead field matrix. I recommend to use a anatomy-based subject-specific lead field if you have one, but if you don't, then TESA will provide a spherical three-layer model-based lead field that you can use to clean the data. And it's doing its job.
before we have the final result, we need to decide how many muscle artifact components we are removing. And the SSPSER function will give us 3 figures from which we can determine this. And here I think all the figures tell the same story. So I would remove 2 components because the first 2 components have this clear broadband response that I talked about being characteristic to muscle artifacts. And similarly, these 2 first components have these sharp initial responses. From the third figure, we can see that the first 2 components explain by far the most power of the artifact signal. And now if we visualize the data, again, we can see that those muscle artifacts have disappeared. Now the cool thing in EEG Lab is that if we write the EEG Lab history, you can see the command that we just used, and you can copy and paste it to your script and use it the next time in your code. And that is exactly what I like to do when I build my own pre-processing scripts.
The second method that we are going to go through today is called the source-utilized noise discarding algorithm that we abbreviate the SOUND. The SOUND is based on very similar ideas as the SSPSER and the similar theoretical concepts that I very quickly went through in the beginning of this presentation. The overall idea of SOUND is presented on this slide. You can read the detailed algorithm from the original article, but the main idea is to evaluate the noise levels of all of our channels through a cross-validation scheme where we utilize minimum norm estimation and then extrapolating the clean signals from the minimum norm estimates. Once we have the final noise estimates for all of our channels, we can form a optimal Wiener filter, a spatial filter, which removes the noise and artifact sources that have topographies that are not likely to originate from intracranial sources.
Okay, so let's look at now an example of the sound algorithm. So again, we are in my MATLAB, and I have pre-processed this example dataset using some very basic steps. But it's clear that there is still some artifact left. Specifically, there are some bad channels that you can see as these long depolarizations. You can see them both in this butterfly plot on the right clearly, and then also in the left in the global EEG plot. So let's see how well sound will perform in automatically finding and removing these artifacts. So again, we can look for the sound tool from the graphical user interface. And here the default settings, which usually work quite well. And you can give your own lead field matrix if you have one, or then you can let Tessa to form the theoretical 3-layer spherical model-based lead field. And the sound has been speeded up quite substantially since it came out, so nowadays it will only take a few seconds for this sound algorithm to clean the data. And we have the results already, so let's see how the plot changed. And quite clearly, the neuronal signals which were underlying, they have stayed intact. We have some nice responses that could definitely be coming from the occipital cortex, which was being stimulated here, but we got rid of the bad channels. And again, we use the graphical user interface, but you can get the code by writing the EEG history. And next time you can clean the data in the exactly same way by adding this command to your script.
So that's it. I hope you found this video useful and informative. If you still have some further questions or you need some further assistance to get started with this method, please don't hesitate to contact me by my email. Similarly, if you find any bugs or problems in the code, reporting them to us would be highly appreciated. In the end, I want to thank all of my collaborators, and with bold, I'm highlighting those who especially contributed in making these methods open access.